Hello, everyone. So glad to be here to introduce the work of high-density scalable cloud gateway for cloud networking. So welcome to join this session. My name is Zhang from Intel. So in the next 40 minutes, together with another Intel expert, Hongjun, so we will introduce you to the basic information of a high-density scalable load balancer, short for HDSLB. So including the background, current states, technical implementation details, as well as the future plans. So we hope that by the end of this session, you're able to have a basic impression of HDSLB. So let's go to the first section, background. So the background of this project is actually the background of the internet era we are in now. So on one hand, the number of devices on the internet is rapidly increasing. And on the other hand, new internet applications are emerging. So these changes made new requests to network infrastructures. So the chart in the middle is a statistical chart of the total amount of internet traffic. It clearly shows that the amount is increasing rapidly as well, and the trend is non-stoppable. So from this trend, we see four specific changes. First is the huge network throughput, the traffic amount increasing exponentially. And second is the increase of concurrent connection numbers. So on one hand, the number of network devices is increasing. And on the other hand, the number of connections of each device keeps increasing too. So combined leads to an extraordinary increase of concurrent connection numbers. And third, inside the data center, so in order to face the challenge of huge network throughput, the interconnect network is migrating from 25 Gbps to 100 Gbps. So it is quite clear that 100 Gbps will become the mainstream interface standard. And the fourth one, with the emergence of HD video, AR and VR, big data, elephant flows, which are single, huge throughput and long-lived connections, are frequently appearing in modern data centers. So these four new specific changes made new requests for the core access device, which is the load balancer at the data center. So after collecting feedbacks and information of industry customers and partners, we made the first design target of HDSLB to solve the performance challenge most of our customers are facing now in Layer 4 load balancer. So you can tell this from its name. It's a high-density scalable load balancer. So the high density means the density of concurrent connections and throughput of a single node. And the scalable means the performance can be linearly increased when you add more CPU resources to it. So our target is for one single node, number of concurrent connection reaches 100 million level, and throughput reaches 150 million Mpps for a short packet, for instance 64 bytes, and 200 Gbps for a long packet. So for a single session, reaches 10 million Mpps forwarding throughput. And besides, also has highly optimized the TCP session establishment performance and the session synchronization optimization between multiple nodes. So after half year of hard work, so Intel development team accomplished the goal well. So HDSLB is able to meet all the requirements of the design target. So the reason why HDSLB can handle this big performance challenge is mainly because HDSLB is a software and hardware co-design based on IA platform. So the optimization is not limited to the software running on CPU. It's a systematic optimization for the whole hardware and software architecture. So we leverage the BIOS configuration, network interface card features, and operating system configurations, and the CPU microarchitecture to squeeze the last job of the performance, unleash the total potential value of Intel product, and then offer the value to our customers. So the current state is that we accomplish every design goal, and now we are cooperating with our top customers to perform POC in their environments. And besides the highlights of performance, so HDSLB also equipped with common features of a load balancer product. Also a brief introduction here. So first is HA, so it supports session synchronization between multiple nodes. And regarding the load balancer mode, HDSLB supports FuNet, DNet, SNet, and DR. And regarding the LB algorithms, it also supports some common algorithms, for instance, RRWLC and constant hash. HDSLB also provides security features and tools for a fine-grained observability. Okay, so after this brief introduction of HDSLB, so next I will hand over the mic to my colleague Hongjun and let him introduce the technical implementation of HDSLB.
Thanks, Yupan. Hello, my name is Hongjun Yi. I'm working at Intel and focus on the VPB and network security. I will continue to introduce the features for the cloud gateway. Now, this cloud gateway is developed based on the DPDK project, which is an open source project, but there are performance limitations on this project and also lack of some features requested by many customers. So we reflect the framework and made huge code changes on this project to make sure it can get more better performance and also rich features to meet the customer's requirements. I will introduce the framework from the bottom to the top. And so far, there are 5 key components in this framework. On the bottom, it's the network device layer. It contains the network interface, such as the DPDK power driver, and also the bounding feature, the VLAN support, and the traffic control, and the KI for the traffic communication between the user space and the kernel. On the second layer, it's the IPsec stack. So it contains IPv4 and IPv6 feature process, and also the IC enable and the routing lookup, and also the ICMP, TCP, etc. On the third layer, it's the key components for this cloud gateway. It contains the scheduling algorithms to schedule the real server for specific features, and also the protocol processing, and also the connection track and the transmit. On the right side, it's the generic infrastructure for this cloud gateway. It includes the message processing with the lockless mechanisms. It also supports the memory pool and also the timer mechanisms to support the flow aging. We also support the flash sync for high availability and also leverage the advanced features for the MacFlow to accelerate the packet processing and also the statics and the configuration. On the bottom, it's the control plane. It contains the IPv6 ADM and also the DPIP to configure the IP address and also the virtual IP, and also the keep alive D is used to keep the cloud gateway and the backend servers to make sure the backend server are alive. So, and we will introduce some key optimization technologies for this cloud gateway. The first one is the batch processing and the vectorizing. There are some steps here. The first one is we put the packet processing pipeline and decompose them into many microjobs, such as the receive and the forwarding microjob, the transmit microjob, the traffic management microjob, and also the timer microjob. And the second step is the vectorizing. In the traditional use case, one package processed from the beginning to the end, and one by one packet is processed. But in our optimizations, we put a package in a frame, and a frame package will be processed through microjobs in batch mode. What's the microjob? The microjob is a subset of jobs for pipelines, and it's optimized to can be fit inside the instruction cache. So as a result, for the first packet in the flow, and the instruction cache is warmed with instructions from a sync microjob, and the rest of the package for a patch will be reused the instruction cache instructions in the instruction cache. So the cost of loading instructions from memory to the cache is a load for each packet. And the final step is packets are processed in batch, and some packets are prefetched into the data cache. As a result, when the packets are processed really, the data cache is warmed by small packets. As a result, the memory access latency is hidden by the prefetch mechanisms. So we can improve the performance by the instruction cache and also the data cache and prefetch. And another optimization technologies we supported is separating the fast pass and the slow pass. In the original DPDK project, the fast pass and the slow pass are put together. So as a result, the performance is not so good. When we benchmark the performance, we found some bottleneck for the slow pass. So we decided to separate fast pass from slow pass. In this diagram, slow pass is used to handle the SNAT feature, the SMP and the IP processing illustrator, and the green part is the fast pass. It can be used for session sync, scheduling, connection track, etc. When a packet comes in, it will be directed by the flow director, and then it will go through the allow list and the parser to pass the packet headers. Then the flow classification model will classify the flow based on the 5 tuple. If this is the first packet for this flow, then the packet will be sent to the session creation to create a new session for this flow. Then the scheduler algorithms will select a real backend server for this flow, and then the packet will be encapsulated and transmitted to the selected backend server. For the rest packets of this flow, it will look up the session table, and because the session was created by the first packet, then a session will be hit in the connection track table, and then the rest of packets will leverage the session information in this entry and encapsulated the requested information and also the backend server. Then the rest of packets will be sent to the same server as the first packet. Besides, when a session is not used, it will be aged out by the session aging mechanism. To support the high availability, we will leverage the added features, the session sync to sync all the features, to sync all the sessions to other servers. Okay, the third optimization we supported is the routing and neighbor optimizations. In the original use case, when a packet will be sent to the backend server, it will look up the route table to get a next hop. Then it will leverage this next hop to look up the neighbor table to get the layer 2 MAC address, and then encapsulate the MAC address and send out the package to the server or the client. In this case, each package will look up one-time routing table and also one-time neighbor table for each packet in this flow. This will lower the performance. So we leverage caching mechanisms to cache the route information and the neighbor entry when we create a new session for a new flow. So when the package of the flow comes in, it will look up the session and get the cached routing entry and the neighbor entry. Then it will encapsulate the routing information and neighbor information and transfer packets to the real server. When the routing information and the neighbor information are changed, we will update the cached routing entry and the neighbor entry to make sure the cached information is updated. To support the high availability, we added the live migration features to our gateway. In this feature, we leverage the multicast group and also the TOR switch to support this feature. In this example, there are 1 active server and 2 backup servers. We built a group, a different matrix group for different CPU core number, such as for core 0 in active server and backup servers. We put them into the multicast group 0. For core 1, we put them into the multicast group 1, and so on. Then, if a new flow is created, is core 0 on the active server, it will build a sync information and send it to the multicast group. And then the T1 switch will forward this multicast message to the backup server 0 and the backup server 1. And the core 0 and the NIC in the backup server will classify this broadcast message and steer it to core 0. When core 0 get this sync up message, it will create an entry into their session table. So as a result, the core 0 in active server and the backup server will have the same session tables. When the active server is degraded or closed for some reason, the traffic will be steered to backup server by the upstream route, and then the core 0 in backup server will continue to process in this flow, and this flow will not be stopped due to some reason. This can help to improve the high availability. Besides, to make sure all sessions are synced, we will leverage the idle time to sync all the sessions in the group. And another new features we added is the elephant flow detection and also distribution. For the elephant flow detection, we leverage innovative algorithms to detect the elephant flow. These algorithms leverages the sampling mechanisms and also optimized heap to help accelerate the lookup time and also reduce the consumption of the memory. For these algorithms, the algorithm will profiles the each flow and also reports the heavy flows with the estimated packet counts. But it won't count every packet in the flow. It just count a small percentage of total packets from a flow, such as 1% of packet in the flow. This is configurable. The key feature in the key point in this feature is that we make the data structure very small, so it can be fit into the local data cache. This can help improve the lookup time. And also, in the original implementation, we just leverage the heap to detect the top N elephant flows. Later, we add a hash table to help accelerate the heap lookup time. So this algorithm is named NIC. It's initiated by Professor Liu from Boston University. Now we are collaborate with him to further improve the algorithm. For the elephant flow processing, except the detection, it also need to support the distribution. In this picture, we put some CPU cores such as core 1, core 2, core 3 into a CPU group. This CPU group will be leveraged to process elephant flow. When a flow comes in to the elephant flow detection model will detect if this flow is the elephant flow. If this flow is a mice flow, then it will go to normal process, and from process is processed from beginning to end in the random accumulation mode in the one CPU core. If it's an elephant flow, then the CPU core will distribute this elephant flow to 3 CPU cores in this group, for example, through a DRB queue. Then packets are processed in CPU core 1, 2, 3 for service processing. Then all the packets belonging to elephant flow will be aggregated into the same CPU core as the receiver core through the DRB, and then it will perform the routing and the transmitted. Here, the DRB is the hardware in the Intel CPU. It can support the hardware load balancer features and also the reordering features. Okay, so far we have introduced the features we have developed, and now we will share the next step for our cloud gateway. The first thing we will support is the elephant detection and distribution with hardware DRB. This is work in progress, and so far we have got some better performance on this. And our gateway can support 100 million sessions. So in this case, IPv6 routing lookup is a performance bottleneck. So we use the novel algorithms to optimize it, and also leverage the AVX512 to accelerate the IPv6 routing lookup. So this work is still on work in progress. Due to the security is become very popular in the enterprise market. The industry introduces their zero trust networking to the networking domain. To support the zero trust network access feature, we are implement the wireguard and leverage the CPU features to optimize the wireguard, and this is under progress. And to provide the insight to the data flow, we will leverage the HyperScan and to identify the high-layer applications, and provide a granular visibility to admin and the customers to make sure they know what traffic or type of traffic is in the cloud gateway. And as a cloud gateway, it's an access point for the data center, so it's be attack target for many malwares. So here we will leverage the HyperScan and also machine learning to help us to detect the malware traffic and also defense it. And there are more features will be introduced to our cloud gateway. So here we will summarize what have we done so far. The HDLCP is a high density and also a scalable cloud gateway running on Intel architectures. It can support 100 million sessions, and the performance can be linear scaled. It reflects the open source DPDK project and ported to DPDK 2011 release, and we can leverage the latest features in the DPDK release. It also leverages many advanced hardware capabilities on the CPU and also Intel NIC to help us boost the performance. And we also separate the fast pass and the flow pass to get better performance gain. The Vectorize and the Microjob helps us to leverage each CPU power to get a better performance. Then the features such as elephant flow detection and distribution, the live migration, help us to address the challenges of the performance, scalability, and the live migration from the industry. Finally, we will, this is a joint effort from many community and guys. Well, thanks to the DPDK community, the DPDK community, and also many guys from Intel, and also the Professor Liu from Boston University. That's all for our session. Thank you so much.